Hi everyone, welcome to my session. Assalamu alaikum. My name is Faisal and I'll be talking today about multi-party computing and decentralized infrastructures. My affiliation is currently I'm a PhD student with Boston University and I graduated from the American University in Cairo. Please feel free to ask questions on the Viva app. I will answer your questions live here. I hope to have this as interactive as much as possible. So I'm going to start my talk by motivating why we need like these things known as multi-party computing by describing a classical problem. This goes back to Andrew Yao, who is one of the founders of this field back in 1982. So he formulated a problem. This problem is about two parties. Let's think of Alice and Bob. Each one of them owns a certain amount of money. Like for example, Alice owns 50 pounds and Bob owns 20 pounds. And they want to jointly compute a function to determine who of them richer than the other. So who has more money than the other. But the trick is that Alice wants to keep her amount of money private, and so Bob wants to. And they don't want to involve any trusted third party into this process. So a naive approach is that you have a trusted third party. Alice and Bob will send their amount of money to this trusted third party, and it will compute the function. But the trick is that I don't want to have any trusted third party. So how can you solve this problem? Another motivating application, and it's actually more real life. So think of a boardroom, for example, a board of executives. This can be like the Egyptian cabinet, this can be the Egyptian parliament, this can be like any a board of a company, and they want to reach a decision about a certain matter. So they start a voting process, and they want the outcome of this voting process to be known to all of them, but without involving a third trusted party. So they want to collectively compute among themselves the result of this voting. So the trick is that you want to compute a function having your inputs private, and you don't want to involve any centralized server or point of trust. A third application is sealed bid auctions. So this is in Arabic زي الأظرف المغلقة for people who do مزادات. يعني if you want to compute an outcome of a certain auction, and this auction is in the setting of sealed bid. So basically each bidder will submit their bid, and the winner is determined according to some procedure. For example, the highest bidder wins. But the trick is that we want to have this process among the bidders without involving a trustee. And same thing with having each bid will remain private to the bidder. So like, if you try to come up with a generalization from these three ideas, think of the problem as follows. So you have a number of parties, P parties. These parties want to compute a joint function on their private input, x1 up to xp. And you have these desired properties. These are folklore MPC properties, but I'm quoting them from Lindel's slides. Number one, you want to achieve correctness. So you want to achieve that when they finish the protocol, the output of the function is the correct output. And you want to maintain privacy, that each input should be known only to its owner. And you want to maintain independence of inputs. And if you want to think of what independence of inputs mean, think of the sealed bid auctions problem. What would happen if one of the bidders actually can set their own bid based on the amount of bid of the others? They won't know the actual values of the other bidders, but they will have some black box that would allow them to actually set their value so that it's slightly higher than the highest bid. So if they can do this, actually, then they can maliciously win this auction. So what we want to forbid here is that each one of these inputs should be independent of the other. The third one is fairness, which means that a party will receive the output if and only if all of the others receive it. Now, how is this important? For example, in the setting of the sealed bid auctions, think of this as follows. So I will engage in the bidding process, and if I find myself not to be the winner, I will actually corrupt the process. I will do, for example, weird things so that we have to restart the auction. So this means that I had access to prior complicated recent classification of parties, but you can read about these on your own. For example, something called covert and other types, but we will not mention these here. Now the adversary itself. So honest, semi-honest, and malicious. These are descriptions of the parties participating. Now, what does the adversary look like? So the adversary is this central devil or central attacker that will actually corrupt more than one node and take control of their private state, and possibly if they are malicious node, they can send whatever messages they want to the other honest player. So this adversary needs to make a selection of the players they want to corrupt. And the selection can be one of two things. The selection can be static, which is basically that the corrupted nodes are chosen prior to the start of the protocol. And once they are chosen, the protocol starts, the adversary cannot corrupt more players. The other adversarial model is, or corruption strategy, is the adaptive strategy. So the adaptive strategy in which nodes can be corrupted as the protocol continues to execute. For example, I can start by corrupting at the start of the protocol. I can corrupt, for example, player 1, player 2, player 3, and then I do some computation, and then, okay, I say I will not corrupt player 3. Okay, so I think they told me that the problem is fixed, so I will continue speaking, and if there is another problem, we'll see about it, but hopefully, let's hope for the best, and I think the problem is resolved now. So as I was mentioning, so Alice and Bob will divide their secrets to the 4 Ninja Turtles. For example, 42 can be subdivided into 11 plus 7 plus 20 plus 4. You do the same for S2. Now, each one of these 4 Ninja Turtles will locally compute the sum of the secrets from Alice and Bob, and they will send this local sum to Splinter. Now, Splinter will add all the local sums to get the value of 110, which is basically the sum of 42 and 16. Now, this very simple process of what we call secret sharing due to Adi Shamir back in 1979, this very simple process of secret sharing now can enable you to actually do multi-party computing by this simple protocol to do addition. Now, if you can do addition and you know how to do multiplication, in fact, we know how to do multiplication, but I'm not going to mention it here to save your time. But it's also a very simple algebraic process. You can multiply 2 numbers in this way. So if you know how to do this process, we know from computer science told us that any circuit can be expressed into addition and multiplication gates. So you can express any computation you can think of as an arithmetic circuit consisting of addition and multiplication gate. And if you know how to do addition and multiplication using MPC, then you can do MPC for any arbitrary circuit. And this was known as the GNW protocol back in the 80s. So now, okay, we know how to do MPC. We know that MPC seems like a fancy idea, but what are real-world applications of MPC? What are actual use cases of people using MPC in our real life? So I'm going to mention 2 very nice examples from what we call using computer science for social good. One of them is actually researching gender pay equity. So these are some of my colleagues from Boston University. I'm not on this project, but it's a very nice project. You can read more about it. This was done in tandem with the Boston Women's Workforce Council. So this is like in Egypt, like in Majlis al-Qawmi lil-Mar'a or other similar entities. So in collaboration with Boston University, they were able to actually collect data from different companies about the salary of employees, men and women, for the sake of actually studying whether there exists a certain gender pay equity between different genders, or and how large is this pay inequality? How can we do better? So the structure was like this. they set a server at Boston University at BU, and the analyst has a client running with browser accessing from the Boston Women Workforce Council. So contributor A and contributor B, you can think of this as companies, for example, company 1 and company 2. So each one of them will take the actual data in this yellow box, add randomness, a random mask to it, which is represented in this blue box, and they will obtain a masked data point. Now they will give this masked data point to BU. Now BU cannot comprehend anything out of this because there is an added randomness and you cannot revert back to the actual value. And they will send the random mask to the Boston Women Workforce Council, and it will be encrypted with us. The Workforce Council can actually add all of these random masks together and subtract it from the aggregated data points to get the actual aggregated data. Now they can't access any certain data point in the clear, but they have access to aggregations and statistics that can help them in their studies. So the first application was actually done at Boston University in joint work with or joint as in not the technical part, but rather the setting and the data analysis with the Boston Women Workforce Council. Now, this other work is also by some of the people working on the other project and other people from other institutions, and it's a use case for using concepts from MPC and similar ideas to identify repeat sexual offenders. So think of this, this is a big problem in campuses, in many universities, in Egypt, worldwide, and everywhere. Usually a sexual offender is a repeat offender. If they commit an offense, they are highly likely to also commit another offense. And research has been done into this from the social sciences. Now for the technical part, we're interested in having a platform for users who are victims of sexual misconduct to actually report to report offenders on this platform while having their input encrypted, but while also offering the capability to match offenders across different victims. So you have encrypted offender name number 1 and you have encrypted offender name number 2, and if they match, you want to involve a privileged communication with the victim, between the victims and a counselor if they wish to engage in such conversation. And actually many universities in the US deploy this system in real world for reporting sexual misconduct, and we hope to actually see such applications of these in universities in Egypt and the Arab region. So I hope these ideas will actually, for young engineers who are interested in doing this either as volunteers or doing this as a project in partnership with universities and seeking sponsorship from the industry, for example, this library, Calypso, is actually available as an open source library on GitHub, and you can also get in touch with the community that sponsors such applications to deploy them in your university. So this is this was the first half of. So the second part of the talk, I'm going to describe a project I was working on with my colleague Kokoris-Kogias, a colleague and mentor, and with Professor Brian Ford and Professor Sharif Al-Qassas from EPFL and the American University in Cairo, respectively. And Liftress, I believe, now moved to Facebook and maybe other places after. And also apologies if you have heard this introduction multiple times when I was connected before, and you're hearing it again, but hopefully you will not face any other problems. So the problem we were dealing with is how to build a privacy-preserving framework for collection of aggregate statistics. So we have this dream of building an ecosystem or a data marketplace for people to have their data being offered to researchers, and for researchers to consume these data points to compute machine learning models, while there is no point in the system that can actually read a certain data point in the clear. So no data point can be seen individually, but rather you're allowed access to the statistics. So what is the use case? You are an application developer, you develop this very nice application, you put it on the Google Store and Apple Store, and people are consuming it, and now you want to collect data and statistics from this application. So for example, if you're the Ministry of Healthcare and you're collecting data from users about the places of spread of COVID-19, maybe you're not interested in the individual data points, whether a certain individual is infected or not, but rather in the collective aggregate viewpoint of the data, and what areas are infected, what areas are less infected, and how can you do better in fighting the virus. So this question of privacy versus functionality is the main theme in this project. How can we leverage functionality and make use of all these, while making use of all of these nice ideas from cryptography about privacy preserving data analytics is precisely the question we want to answer. Now there are also other questions such as how can we make this system easy to view by the user, and the user can easily edit the access control privilege on their data. For example, if I'm a patient and I have medical records, I want to have my doctor and my hospital to access this data, but I don't want my university or school or workplace to access this medical data. And by access here, we mean access in an aggregate form. So even in our framework, we're not interested in single data entry view of data, but rather the aggregate. So when I mean that the doctor can access my data, it means that they can access it even in aggregate form. So for example, as a median with other patients, or as in a global study they are doing about a certain disease or something like this. The third challenge is this theme of decentralized trust. Now, as you all know, the blockchain is here, it's shaping our future. It's this big new thing that will do many things, but you should be careful with this, because some applications need it, some applications need other things that may be more critical. But the blockchain is nice. I believe that the blockchain can do many good things. So this notion of decentralized trust, back in the old days, we used to trust each other locally. For example, I am your neighbor, I trust you, we can do exchange of goods. I can give you, for example, rice, you can give me meat, and this is how things used to do before we had banks and other institutional organizations. So once we had banks and these sort of like trusted entities, the trust model went from a local trust model to an institutional trust model. Now with this all hype of blockchain and large economies, we have this notion of distributed trust. I don't trust a single person, but rather I trust maybe a collective set of people. So the fourth challenge now is this thing called robustness against bad clients. So for example, if I am a developer and I deployed an application for healthcare, and I'm interested in collecting people's heartbeat. So people can have a heartbeat of 70, 100. These are in the valid range, so maybe something between 0 and 200. But if someone is giving you a heartbeat of negative 42 beat per minute, maybe you should be suspicious about this. And it's not only that the user could be malicious, but also the user could be using a machine that was hacked by a hacker, and this hacker is sending malicious information through the application to dilute our statistics and view of the population. So we should be able to filter good data from bad data. Now this could be a trivially looking task. I want to filter good data from bad data. I could write a Boolean function. This function will take the data point and output true or false. But the problem is more than this. I want to be able to do this filtering while actually not looking on the data. So the data should be kept private. And based on this, I will do some interaction with the user, and based on this interaction, I will accept or reject the data point. So I'm basically executing, if you know what the term zero knowledge proof is, I'm basically executing some sort of a zero knowledge proof to make sure that the data point is valid. Now, failing and going malicious is not only about users, but also servers can be hacked, servers can fail, servers can have corrupt people manipulating them. So we should also be careful about this. The challenge number 5 we're interested in is auditability. So we want to have the system to have some sort of a public way of auditability. So we want to have the public, the general public, to be able to look on the trails of the system and the data access logs and be able to actually validate that the system is not misbehaving. And challenge number 6 is about this concept of fair exchange of data. You can envision the system as a marketplace for data points. Instead, for example, of having Facebook or any other social media platform collecting profits based on your data, you're actually in control of your data. So if, for example, an advertising agency uses your data, maybe you should actually get some value for the data you provide. So you want to prohibit two scenarios. You want to prohibit a scenario where the data consumer takes the data and not give any value to the user, and you also want to prohibit this scenario where you actually pay the user and the user doesn't give you anything back. So you want to have this notion of fair exchange of data. So these are some motivational challenges, motivating applications and challenges of this problem. But now we're going to look carefully about who's at stake in this system, in this ecosystem. What are the parties involved? So number one, we have the data providers. So the data providers are normal users. These are the users who provide their data. And this could be normal end users, just a single user, or it could be a corporation providing sensitive data. The second type of entity in our system is a data consumer. So the data consumer is this researcher or this advertisement agency or whatever that is interested in obtaining an aggregate view of a certain population. And third, we have the storage provider. So the storage provider have no interest in the plain text data, but they offer the infrastructural services for the data providers and consumers, and they give some promised guarantees. Now the computation nodes are entities who actually provide computation infrastructures and also have no interest whatsoever in the actual data. Finally, we have public verifier. These could be normal people. This could be any one of these entities, but they are mainly interested in making sure that the system is being used properly and no misbehavior is happening in the system. So to recap, what are the system goals we want to achieve? We want to achieve access control. Users should have revocable and fine-grained access control over their data. We want to achieve privacy of confidential data points, and also privacy for the data consumers. So if you're a data consumer, if you're an advertisement agency, or if you're, for example, if you're company X and you have a competitor, company Y, and let's say that you paid to get an aggregate model, you don't want your competitor to actually have access to this model. So we give privacy not only to the data providers, but also to the data consumers. We want to achieve, as I said, a fair exchange of data. You have data consumers, they are paying the data providers, and the data providers are giving data to the data consumer. And we want to have this occurring in an ecosystem that is fair to all users. We want to achieve robustness, that this model should be live even when single nodes fail or become malicious. And as with the theme of the talk since I started, we don't want to have any single point of compromise or failure, and we want to have the system to be auditable by providing publicly verifiable template-proof access log for data accesses. So now this is a very nice meme that says how people can differently approach this kind of problem. So scenario number one is that you say, okay, I will go to a trusted third party, someone we trust. I will tell them, okay, we will give you all the data and you will give us back all the computation. And this is not using any crypto, we're just doing it the old way. You can go one step further. There are systems that use trusted hardware, so they reduce the problem to some problems that are well-defined, and these sub-procedures that are well-defined are executed using trusted hardware. Now that's the final approach, which is the one we're going to use, is that actually you're going to use cryptography to actually build such a system. So we're not going to trust anyone. We're going to be only trustful in our assumptions about the system and the threat model we define. Part of this talk, I'm going to mention things about blockchain, and I'm sure almost all of you now know some sort of a description of what blockchain is, but I'm going to give a sort of description for people who don't know or people who want a quick recap. So imagine a blockchain as a public or a permissioned sort of a log for certain transactions, and this log is designed in a way that it's tamper-proof. You can tamper with its entries. The way it works is that a transaction is requested to be put on the blockchain, and a block representing it is created. Now this block is represented out to is distributed to the whole network. For example, the Bitcoin network or the Ethereum network, and nodes will validate this transaction. Once they agree that this transaction is valid, each one of them will receive a reward for this work that they did for the good of the whole network, and this block is added to the existing blockchain, and the transaction is marked as complete. So I'm going to use some of these ideas I mentioned previously to build what we call a Strawman design. A Strawman design is like a prototype or like an initial design that we're going to improve on. So this is a system by Lefteris and others from the DDIS lab. It's called Calypso, which is basically an auditable sharing of private data over blockchains. So this provides a way for data consumers and data providers to live in an ecosystem where data providers can share data and data consumers can access it. And they use a blockchain for managing these kinds of transactions. So the scenario, for example, Wanda is a data owner. She has a data point. This could be her medical information. She wants to publish it on this network. So there is what we call the access control cothority. And cothority here is just a fancy term for a collective authority, which is basically a cluster of nodes that have a shared common task. So Wanda will give her data point encrypted along with the access policy for her data. She will say, okay, I want my doctor to access this data point and I don't want my school to access it. And she will give this to the access control authority, and the access control authority will verify that this is a valid right transaction, and if it's valid, it will be added to the blockchain. So you have here a blockchain of secrets. Now Ron wants to have access to the secret, so he will request access to the secret from this authority, and in step 2.2. Now if they have the needed privilege, if Wanda had authorized Ron before, there will be a proof of a read transaction. Now Ron will take this proof of read transaction and go to the secret management authority, which is another authority that is capable of re-encrypting the secret from its current state to a state where it's encrypted using Ron's public key. So Ron هو حط الطلب بتاعه على البلوك تشين is validated الطلب بتاعه. بعدين السيكريت مانجمنت اوثورتي هي الجهه اللي هتقدر ان هي تحول السيكريت من انكريبشن بالبابليك كي بتاع الاوثورتي للبابليك كي بتاع رون. فكده اصبح ان رون معاه السيكريت ري انكريبتد. لو بصينا على الشكل ده, if we look at this system, we will see that Ron has access to the plain text data point. But what is the gain? The gain is that we have verifiable way of making sure that transactions, read accesses, write accesses are properly maintained in the system. So I'm going to build a Strawman design based on this system, and I have these 5 goals. These 5 goals are for Calypso, which is not my work. This is a prior work to the work we are doing. So Calypso has these 5 properties. They are confidentiality of secrets, except for authorized personnel, auditability of the whole system because it's using blockchains, and atomic data delivery, and dynamic identities. Dynamic identities basically means this thing called skip chain on top of Ron's head. So this skip chain is basically a way so that Ron can refresh their public key. يعني Ron, if they want to change their public key, they can, for example, they had a public key 1, and for some reason their public key, their private key has been leaked. So they can actually change their private and public key pairs in the system by adding a new pair to the skip chain of identity. And of course, the system is decentralized. As you can see, there is no single point of compromise or failure. All of these are clusters of nodes and not a single computer or machine. So I'm going to say, okay, I will use Calypso as a vanilla system to store and retrieve data points. And I'm going to have the machine learning part done centrally. And in this case, data points will be collected in a publicly auditable, access controlled fashion. So what I'm doing is that I'm taking the machine learning process, I'm doing it centrally on the node, and they have all the data and they build the model locally. The problem with this, of course, is that data consumers can see the actual plain text data points. So what properties did we achieve? We achieved access control, لأن محدش يقدر يaccess غير people who are authorized. We achieved fairness because basically Ron can access a data point يعني if and only if the transaction is completed in the system. So basically this means that if the transaction is completed in the system, only then can Wanda receive her payment and Ron access the data point. You can have auditability by virtue of the blockchain in the system, and the system is partially decentralized because we have the access control and secret management done in a decentralized way, but still the machine learning part is done centrally. We don't have privacy because Ron can see all the data points before building the machine learning model, and we don't have robustness against bad clients because basically we are not verifying the data point. طيب we don't have robustness. Robustness هنا معناها ايه؟ معناها ان I want الداتا بوينت اللي جايه من واندا انا عايز اتاكد ان this is a data point that is in the valid range. How can I do this? As I mentioned, we can do this using zero knowledge proofs. So we use a certain type of zero knowledge proofs from a paper by Corrigan-Gibbs-Boneh. So they proposed a decentralized system for computing aggregate statistics, and this decentralized system will provide client privacy as long as there is at least one honest server. So you have a set of servers. This set of servers will compute on data points, and because the data point is secret shared among the servers, so الداتا point الواحدة متوزعة. يعني بمعنى إيه؟ بمعنى إن in the figure you see الموبايل فون بيقسم السيكرت بتاعه into shares، هيبعت لكل سيرفر شير منهم. السيرفرز ما تقدرش تعرف، ما فيش حد فيهم يقدر يعرف الداتا بوينت هي ايه طول ما في واحد فيهم اونست. طول ما في واحد فيهم اونست و will not collude مع الاذرز، they won't know the input of this individual data point. وهم عشان يقبلوا data point they first, as you can see in figure 1b, they have to verify it first. they first run a zero knowledge proof عشان يتأكدوا ان data point دي is a valid data point. After its valid data point, they can compute a function f. This function can be aggregation. For example, they can compute a mean. They can compute, they can find the average. They can find standard deviation. They can find the sum, the maximum, the minimum. They can compute simple aggregate statistics and linear models. In this paper, Corrigan-Gibbs-Boneh, they only considered linear models. You can expand beyond linear models, but you will lose some of the efficiency that they gained in this paper. طيب ايه الفكره الثانيه؟ احنا we want to take the first system that we proposed, we want to take it one more step. I will combine Calypso with Prio to get decentralized design. Now I will go to a fully decentralized fashion. With Prio, because of the zero knowledge proofs in Prio, I will be able to validate data points. And because the Prio servers will compute for the data consumer will only have access to the model and not the individual inputs. So as you can see in figure 1d, this is done between the servers collectively, and then they send the function to the data consumer. طيب نبص على الشكل الحالي للسيستم. احنا عندنا الداتا بروفايدر عندهم داتا بوينتس، الداتا كونسيومر عايز يبني موديل، وعندنا 3 clusters of nodes: access control, secret management, and aggregation. Each one of these has a task. Access control has this task of making sure that the points have proper access privilege and only those who are authorized can access the data points. طيب السيكريت مانجمنت كوثوريتي بيعمل ايه؟ السيكريت مانجمنت كوثوريتي it will take it's able to re-encrypt secrets from their shared public key to public keys of certain entities. طيب الاجريجيشن كوثوريتي can do validation of data and computation. يقدروا يحسبوا linear regression، يقدروا يحسبوا standard deviation، يقدروا يحسبوا average وهكذا. First point, the data provider will publish their secret shared data point, and then the data consumer will request access for many points from the access control authority. The access control authority will check the privilege of this data consumer and reply by granting access to only the authorized points. Now they will request the secret shares from the secret management authority using the proofs they obtained from the access control authority. So they are already authorized to access the data, and they get a proof that they are authorized. Now they will take this proof, go to the secret management authority, and tell the secret management authority, I have a proof that I can access this. Can you please re-encrypt these for me? So it will send back encrypted secret shares. And now there is a catch to this. So these encrypted secret shares are encrypted as a whole for the data consumer, so that no one in between can actually see these. But each one of these secrets is encrypted inside. So you have a big envelope, and inside this big envelope you have a smaller envelope for each one of these nodes in the aggregation authority. يعني عندنا encryption كبير لكل الداتا بوينتس بالكي بتاع الداتا كونسيومر. Inside this big encryption في encryption لكل data point بحيث ان كل شير يبقى encrypted بالبابليك كي بتاع الاجريجيشن authority corresponding للشير ده. The data consumer will take all of these points and initiate the Prio protocol to compute aggregation. Aggregation authority will compute local aggregators and send to the data consumer. Now we're deviating يعني في تعديل شويه على البرايو بروتوكول في ان احنا بنعمل ايه؟ الاجريجيشن authority بدل ما تحسب الفانكشن اوتبوت كل واحد فيهم هيحسب لوكال اكيوميليتور ويبعته للداتا كونسيومر. ده هيخلي ان الداتا كونسيومر will be the only one to have access to the final model. يعني حتى الاجريجيشن authority will not have access to the machine learning model that the data consumer requested. This means that بعد كده الداتا consumer can combine all of these local aggregators to get the final model. So as I said, the aggregation authority doesn't have access to the final model, but rather the data consumer. يبقى in this model no single server أو computation node أو any point in the system have access لsingle data point ولا غير الداتا بروفايدر اللي هو صاحب أو صاحبة الداتا بوينت دي. ولا server أو ولا computation node in this system has access to the final model except for the data consumer who requested this final model. طيب ايه properties so far? We have access control, we have fairness, we have auditability, decentralization, privacy. The final remaining challenge is robustness. Robustness بمعنى ايه؟ Robustness against malicious servers. The Prio protocol can designed ان هو يبقى robust, can design to obtain privacy, but there are ways that you can play with the Prio protocol so that it's robust against failing servers. So we do this by asking ourselves how can we make the system tolerate a faulty minority. So the SNPs, which are the secret shared non-interactive proofs, اللي هي proofs of zero knowledge proofs in the Prio protocol, these are a multi-party computation of a certain arithmetic circuit. So if we could only replace this circuit by an MPC that is fault tolerant, then I'm able to obtain a fault tolerant system. And in fact we can do this. هيحصل عندك شوية loss في ال privacy parameter وشوية loss في ال efficiency. بس you can do this. So if you use an MPC protocol that is tolerant against a faulty minority, you will overcome this problem. طيب So in this final system, after all these modifications, we obtained all of the properties we need: access control, fairness, auditability, decentralization, privacy, robustness. So we have this big data marketplace that can allow people to access data points in aggregate forms من غير ما يشوف individual points. طيب. We did a small demo. We have breast cancer data. This data set containing information about patients and healthy cases, their age, BMI, glucose, insulin, etc. As a task is to build a model that will predict how likely a person has breast cancer given their medical information. But the catch is that I want to maintain the privacy of all the study participants. So I'm computing a linear regression classifier, machine learning model that can classify people into cancerous versus non-cancerous based on these parameters. But I want to do the training so that I don't see individual data points while training. يعني من الآخر I'm training a model. الموديل ده هيقدر إن هو يتعلم من individual health data من غير ما يشوف كل data point لوحده، بس هيشوف الفاينل output. We did this on a local machine with a breast cancer data set, and as you can see, the green part is the overhead of the Prio protocol, and this yellow part is a very small amount. This is just what you would have done without our system. So our system adds this overhead in time. You have some time for the transaction proofs in blue, and some time for the Prio protocol in green. So this added overhead is justified by the privacy gains that you get. And you can also play with these parameters. In fact, this is an ongoing work, and we hope to reduce these by playing more with the parameters. There are some parameters in the underlying blockchain, such as the block interval and others, that we can reduce this time to more reasonable parameters. This is another showcase of how the delay will go if you increase the number of nodes in the system. So if you have a cothority of 4 versus a cothority of apologies. This is for the dataset size. So if you increase the dataset size, you go from 500 instances to 3,000 instances, you can see the blow up in the time it takes to train the model. Here you can see the blow up in the time it takes by increasing the number of hosts. So I have 4 hosts, 4 servers, up to 16 servers. There are related works in the literature. There is something called Enigma. This was, I think, introduced back in 2015, maybe a bit earlier. But they introduced a decentralized data marketplace. Our system is different in the sense that the Enigma considered a model where the storage provider is not guaranteed to deliver to consumers. Another system is Droplet, which offers decentralized authorization for efficient access. It's tailored for IoT applications, but it assumes that the storage provider is a highly available entity that will not refuse to serve data to consumers. And in our case, we don't have any trust in people, even the storage provider and data consumers, because everything we do is on chain. There is nothing that a single party will have possession of. Latest one is, as far as I know, is Sterling. Sterling relies on trusted hardware and trusted execution environments to get some of the security properties. In our system, we don't rely on any trusted hardware assumptions. So in conclusion, I'm going to conclude my talk by talking about this system. So this system, as you have seen, it's a fully decentralized, fault-tolerant machine learning framework that's fair and private and auditable and robust. It's the first system, to our knowledge, that actually achieves all of these properties without reliance on trusted hardware. And we have some quick demo, and we're also working on updating it using the Bitcoin distributed ledger. It's some internal blockchain to the EPFL lab I was working in. And we integrated this with the Calypso service to get and the Prio MPC primitives to implement the system in Go. As you have seen, we have benchmarked this against different dataset sizes, and it's ongoing work, and we hope to achieve more in this front by working on more challenges. And in general, not only about our project, as you have seen before, I started with the second part of the talk. In the previous part, we had good examples from people from Boston University and other places doing good things with MPC and this decentralized infrastructure and how they can be used for the social good. So I'm going to conclude by talking about this. Maybe I can switch to Arabic. يعني ازاي ان احنا بنأمل ان التكنولوجيا دي تبقى متاحة في مصر والعالم العربي. يعني تكنولوجيا الديسنتراليزيشن وتكنولوجيا الام بي سي، الحاجات دي كلها can be used to give users more assurance، يعني تدي المستخدمين حماية أكتر. يعني مثلا تبليغ عن أي حاجة عن طريق الام بي سي سيستم، هو هيخلي البيانات بتاعته محفوظة في أمان، بس هو احنا مهتمين بالصورة العامة. مثلا في مكافحة كوفيد 19 أنا كل واحد هيبلغ إن هو مصاب، بس أنا مش عايز، هو خايف على الداتا بتاعته، هو مش عايز الناس تعرف إن هو مصاب، بس أنا لا، أنا هقول له أنا هديلك الأمان إن أنت بس إحنا مهتمين بإن احنا نعرف الشكل العام لانتشار الفيروس وليس البيانات الشخصية. بتستخدم في الشركات والبنوك. البنوك مثلا هو كل بنك بيبقى عنده ريسك اناليسيز موديلز انترنال ليه. مثلا بنك الف وبنك ب، هم كل واحد فيهم عنده ريسك اناليسيز موديل انترنال، وهم عايزين يحسبوا مع بعض جوينت ريسك اناليسيز موديل. يعني عايزين يعملوا مع بعض جوينت ريسك اناليسيز موديل، بس كل واحد فيهم طبعا عشان البنوك والكلام ده ممكن يبقى فيه بعض الكومبيتيشن او بعض القوانين اللي بتلزمه ان هو ما يطلعش بيانات العملاء بره. فازاي ان هو يقدر يعمل جوينت ريسك موديل من غير ما ان هو يطلع البرايفت داتا بتاعته بره الاورجانيزيشن بتاعته. يعني مثلا عندنا 4 بنوك هيعملوا زي تحالف ان هم يقدروا يحسبوا جوينت ريسك موديلز ويقدروا يستطلعوا الماركت مع بعض، بس من كل واحد فيهم يحتفظ بالبرايفت داتا بتاعته. فالتكنولوجيا، يعني التكنولوجيا بتاعت اللامركزيه او الديسنتراليزيشن والام بي سي ليها مستقبل كبير في مصر. وانا شايف يعني عامه ان مع اهتمام سواء الشركات او الافراد او الحكومه بالتكنولوجيات مثلا زي البلوك تشين، وان هم بدا يبقى فيه اهتمام اكبر في الوطن العربي عامه بالتكنولوجيات زي كده. اتمنى برضو يكون فيه اهتمام بالحاجات اللي فيها كريبتوجرافيك ابلكيشنز زي الام بي سي والكلام ده، وان يبقى في قاعده من الناس ان هي بتشتغل بالحاجات دي بحيث يبقى ليها ريل وورلد ابلكيشنز في مصر زي ما هو، والعالم العربي زي ما متواجد في 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 الاماكن المختلفه من العالم. ويكون في يعني ان شاء الله الشباب يبقى في الرياده. واتمنى لو في حد مهتم خصوصا من الناس الحاضرين، يعني الساده الحضور، لو حد عايز يتواصل معايا او عنده اقتراحات لمشاريع زي كده، طبعا ان شاء الله هتبقى يعني حاجات كويسه. وشكرا جدا على اهتمامكم، واتمنى تكون التوك يعني كانت مفيده للناس، وان هو يكون في بعد كده ان هي تكون اثرت في حد ان هو هيشتغل في مشروع زي كده، او ان يبقى في اورجانيزيشن شايفه الكلام ده وعايزين يستخدموا التكنولوجيا دي في الشغل بتاعهم. وشكرا جدا ليكم. طبعا معلش ان هي المشاكل التقنيه اللي حصلت والموضوع اللي هو فيرتشوال صعب ان لو في حد عنده سؤال يتكلم او كده. فبس طبعا الووفا اب موجود، انا ممكن انتظر دقيقه لو في حد هيكتب سؤال في الووفا اب، يعني ممكن نتناقش فيه معاكم يعني اونلاين. ولو في اي حاجه تانية بعد التوك ممكن حضراتكم تبعتوا لي على الووفا اب او الايميل بتاعي islam@bu.edu، او الويب سايت بتاعي او اللينكد ان اللي هو موجود في الووفا اب. يعني اتمنى ان نتواصل مع اكبر قدر ممكن يعني من الساده الحضور ان شاء الله.